In this video, we're going to look at partial fraction decomposition to be able to help us integrate rational functions. We're going to be able to recognize linear factors, repeated linear factors, and quadratic factors in rational functions. This allows us to take a rational function that may not be on first inspection very easy to integrate and break it down into smaller pieces that allows us to integrate much more quickly. So we're going to start with what we learned back in probably Algebra 2 or Algebra 1 in your high school math course. We're going to start by adding these two fractions or these three fractions by finding the lowest common denominator. So the lowest common denominator for the first example is x multiplied by x plus 3. What we would do back in our Algebra 1 or Algebra 2, or where you learn this, is you would multiply each fraction by whatever value, whatever factor of the lowest common denominator is missing to produce the lowest common denominator. So you can see on my first fraction, I multiplied numerator and denominator by x plus 3. In my second fraction, I multiplied by x, numerator and denominator. In the numerator of my first fraction, I'm going to get 2x plus 3, x plus 3, plus x over x, just x squared, just x squared. And don't forget, I do need an x right there as well. And then we have x plus 3. Now, we can see in the numerator, I'm going to get 2x plus 3 plus x squared. And in the denominator, I'm going to leave it as x plus 3. Now the numerator, I'm just going to reorder it. So it's x squared plus 2x plus 3 all over x plus 3. What we are going to do, by the way, is we're going to go backwards. This is just a nice review on how to go forward, but we're going to go backwards. We're going to be given this, and we're going to try to get to here so that we can integrate it. Let's do one more. Now the lowest common denominator here is going to be an x squared and then an x plus 3. This last fraction is missing the x squared. This middle fraction is missing the x plus 3. And this last fraction is missing the x and an x plus 3. So I'm going to end up with 2x squared plus 6x. And then I'm going to have plus 4x plus 12. Oh, excuse me, that is a minus there. I wrote over that, so that should be a minus. So a minus and a minus. Subtraction there. And then I'm going to have plus x to the third. And then in the denominator, I'm going to get x squared, x plus 3. Now I'm just going to combine up like terms and reorder it. X to the third plus 2x squared plus 2x minus 12 all over x squared, x plus 3. So we're going to talk about now the partial fraction. Suppose we have this rational function p over q. Then I can rewrite this rational function with a1 over x1x plus b1. And this is when we have non-repeated linear factors. And what I mean by linear factors and non-repeating, if I look at this first example, my linear factor was x and x plus 3. Those are two linear factors, and they're non-repeating. If I look at my second example here, I have a repeating linear factor, which is x squared. The first linear is x, the second one is x squared. So this is repeating, and then x plus 3. So this partial fraction decomposition has non-repeating, so it would only apply to my first example here. It wouldn't apply to my second example. So as an example, suppose we had, and I'm going to do something fairly straightforward, 3x plus 5 over x minus 1, x plus 2, and x minus 5. I would rewrite this as a sub 1 over x minus 1 plus a sub 2 over x plus 2 plus a sub 3 over x minus 5. And that's how I would write it, and then we will learn how to find the A1, A2, A3 in a moment. Here's a nice problem-solving strategy for solving partial fraction decomposition. Now, once we have set up the partial fraction decomposition and we have clear denominators, and I'm going to show you how this is all going to work in a moment. If we take this example, we know any coefficient on the left-hand side has to match the coefficient on the right-hand side with the same powers. So I know that a must be equal to 1 because these are the coefficients on the x to the 5th. If I then look for my x to the 4th, I know that b has to equal 3 because I'm looking at the coefficients on x to the 4th. My x cubed, so x cubed, I'd have 2 is equal to c, and you can see how this works. So let's start with the partial fraction decomposition with my first example here. So I would first factor. That's the first thing you want to do is factor the denominator. So I have 2x over x minus 1, x plus 1. Now you can see the denominator is non-repeating linear factors. So I would write this as a sub 1 over x minus 1 plus a sub 2 over x plus 1. And if you prefer to use a, b, c, you absolutely can. And what I mean by that is you don't want to do subscripts. That's cool. You don't have to. You can call this a and you can call this b. And that's totally fine if that's what you would like to do. Now once I have it wrote as 2x is over the x minus 1 multiplied by x plus 1 in my partial fraction decomposition with non-repeated linear factors, then what I'm going to do is I'm going to multiply everything by the lowest common denominator. And you can see it's going to be x minus 1 and x plus 1. Now this is an equation. I'm assuming one side is equal to the other, so I don't have to find the lowest common denominator of each one and make single fractions. I still need to find the lowest common denominator, but I don't need to find the single fraction is equal to a single fraction. Rather, what I'm going to do is I'm going to multiply every single term on both sides of the equal sign by the lowest common denominator to clear my fractions. So I have x minus 1 multiplied by x plus 1. And you can see these denominators will cancel. The x minus 1s cancel. The x plus 1s cancel on that one. And my final term. And what I'm going to end up with is 2x is equal to, I'm going to have an a, x plus 1, plus b, x minus 1. Now, I'm going to go ahead and multiply the the right-hand side through. So I have ax plus a plus bx minus b. I'm going to reorder this so that I have my x's together and factor out the x's. So that any term that has the x, so I have a plus b would be multiplied by the x. And that comes from this ax and this bx. I'm going to get my constants together. So I have plus a minus b. Now, you can see that there is no constant here, so if we start with our constants, we have a minus b is equal to 0. And we also have, with the x term, I'm going to have a plus b is equal to 2. So now I started with a rational function. Then I did a little bit of factoring. And then I canceled denominators, and now I'm in the land of linear equations. I have two equations and two unknowns. From this first equation, I know that a equals b. If a equals b, then for the second equation, I have a plus a is equal to 2. So 2a is equal to 2. That means a is equal to 1, which means b is equal to 1. Okay, so I'm still not done. All I've done is I found the coefficients in the numerators of my partial fraction. So to answer the question, then I'm going to come back and I'm going to say this 2x, x squared minus 1 is equivalent to 1 over x minus 1 plus 1 over x plus 1. And there is my partial fraction decomposition. Let's do another example. So I'm going to start with b. And with b, first thing I'm going to do is factor. I have to factor the denominator. So I have 11x squared minus 5x minus 10 over, I'm going to factor out a 5, I'm going to factor out an x squared, leaving me x minus 1. Now when I do this partial fraction, I'm going to bring this 5 with this x minus 1. As long as it's on one of the factors, it doesn't matter which one. I find it less confusing if you put it on the singular versus the repeating. So this will be a over x plus b over x squared, because it's a repeating, and then plus c over 5x minus 1. Now we can see our lowest common denominator here is going to be x squared and a 5 and an x minus 1. When I multiply each term by my lowest common denominator, I'm just going to erase this so I have space. I'm going to be left with my left side, which is the 11x squared minus 5x minus 10. And on the right-hand side, I'm going to be left with an a, 5, and an x. Let me erase this as well. Get rid of that. And I will have a plus 5b and x minus 1. Oh, and this one also should have an x minus 1. And then plus c, and then this is going to be x squared. So I have 11x squared minus 5x minus 10 is equal to, I'm going to have 5ax squared, distributing the 5a through, and then minus 5ax. And let me erase that. And then I'm going to have plus 5bx minus 5b plus c x squared. 11x squared, 5ax squared, and plus c x squared all need to be equivalent. So I have the 11, that's the coefficient on the x squared, is equal to 5a, that is the coefficient on the other x squared, plus c, that is coefficient on the other x squared. Now looking at my x's, I have negative 5, negative 5ax, and plus 5b. And then for my constant, I'm going to have negative 10 is equal to negative 5b. 3 equations, 3 unknowns. I'm going to start with a constant because I have b is equal to 2. Once I have b is equal to 2, I can substitute that into here. So I have negative 5 is equal to negative 5a plus 5 multiplied by 2. So I'm going to get negative 15 is equal to negative 5a. A is going to be equal to 3. I can back substitute it here. And I have 11 is equal to 5 multiplied by 3 plus c. So I have 15, bring that to the other side, subtract 15 from both sides. I'm going to get negative 4 is equal to c. So my partial fraction then, I found my a to be 3. So I come back over here and I say a is 3. So a is 3. I found b to be 2. So this is 2. 2. And I found my c to be negative 4. Negative 4. Let's take a look at D. C is going to be similar. I'm just going to give you a heads up on C. With C, we realize that x minus 2, if I factor out a negative 1, it becomes negative x plus 2. So same thing as if I have 2 minus x, if I factor out a negative 1, it becomes negative 2 plus x, which means these can switch positions. The negative 2 and the x can switch positions, and x minus 2. So this really is this with a difference of a negative. So my denominator can be wrote as 5x plus 4 for the numerator, a negative x minus 2, the quantity squared. Now I personally would bring the negative into the numerator, and so I'd have a negative 5x minus 4 is equal to x minus 2. And then of course when I start to break this up, it'll be a over x, that should be squared, b over x minus 2 plus c over x minus 2, the quantity squared. Now, for d, now d is the one I wanted to look at. I wanted to jump to d because when I jump to d, I see that the denominator, both the x squared plus 2x plus 9 and the x squared plus x plus 5 are both irreducible quadratics. I can't factor those over the real numbers. So if I can't factor those over the real numbers, this is how we address that. So I have 2x squared plus 3x plus 14 over the x squared plus 2x plus 9. I have x squared plus x plus 5. When I break down this partial fraction, I'm going to write this as a sub 1x plus b sub 1. This is where I actually will use subscripts because I have to have 1 degree less than what is in the denominator. Now notice here my degree is 1, so I used constants. So this is a degree 1 with constants. This is a repeating degree 1 with a constant in the numerator. Because this is an irreducible quadratic, I need to have a linear in the numerator. So I have x squared plus 2x plus 9 in the denominator plus, I'm going to use a sub 2 plus x plus b sub 2. And then in the denominator, I'm going to have x squared plus x plus 5. Now, if you want to use a, b, c, d, absolutely do so. There's nothing wrong with doing that. I'm just using the subscripts so you can see a little bit easier where the coefficients on the x on the right-hand side are and what the constants are on the right-hand side before I do the multiplication of the lowest common denominator. Now my lowest common denominator, of course, is going to be x squared plus 2x plus 9 multiplied by the x squared plus x plus 5. When I multiply every term by the lowest common denominator, my right-hand side is going to be 2x squared plus 3x plus 14. And then on my right-hand side, I'm going to have a sub 1x plus b sub 1 multiplied by x squared plus x plus 5. And then I'm going to have plus a sub 2x plus b sub 2 multiplied by the x squared plus 2x, x squared plus 2x plus 9. And once again, I will distribute out. So I'll distribute this through. I will distribute the b sub 1 through. I'll distribute the a sub 2x through. I will distribute the b sub 2 through. And then I will combine up like terms and get a system of equations. This is a place, if you remember matrices, this would be a place where you're like, man, I'm just going to use matrices. Cool. If you don't remember matrices, you can use the system and do elimination or substitution. This one was a nice, easy substitution. I'm not going to finish this off, but I am going to tell you what the answer is. And when I get totally done, the answer is going to be, let me erase this, is I'm going to get 1 over, 1 over, and 1 over. Now, let's go ahead and start doing some solving with partial fraction decompositions where it is appropriate. So if we take a look at a, the first thing I'm going to do is write this as 1 over x minus 3, x minus 2 is equal to a over x minus 3 plus b over x minus 2. Multiplying each term by our lowest common denominator, which just happens to be x minus 3, x minus 2, I'm going to get 1 is equal to a x minus 2 plus b x minus 3. So 1 is equal to ax minus 2a plus bx minus 3b. 0 is equal to the a plus b, because this is my x term. My constants give me 1 is equal to negative 2a minus 3b. From this first set of equations, or this first equation, I'm going to get a is equal to negative b. So going down here, I have 1 is equal to negative 2 multiplied by negative b minus 3b. 1 is equal to 2 minus 3b. 1 is equal to negative b. b is equal to negative 1. So my integration of 1 over x minus 3, x plus 3, excuse me, x minus 2 dx can be wrote as the integration of, if b is equal to -1, that means a is going to be 1. So 1 over x minus 3 plus -1 over x minus 2 dx, which is the integration of 1 over x minus 3 dx minus the integration of 1 over x minus 2 dx, which is the natural log of the absolute value of x minus 3 minus the natural log of the absolute value of x minus 2 plus c. If I want to, I can bring these back in using the laws of logs, and if I'm inclined, this would be the natural log of the absolute value of x minus 3 over x minus 2 plus c. However, I want to say that I am perfectly happy taking this as an answer, or if you want to bring it back together, you can write that as an answer. So that is the first one. Let's go ahead and jump to one of the other ones. I will give you the answers to these other ones, but I want to jump to C because C is slightly different. So I'm gonna focus in on C, and before I do that, I'm just going to come over here and I'm going to erase this because I'm going to need the space for C. I will give you the answer to B here in a moment. Just let me erase. Continue to erase. Okay. So I will give you the answer to B. I'm just going to I'm going to tell you how you're going to set this up again. This is going to be 1 over x squared minus 1, 1 over x minus 1, x plus 1, a over x plus b over x minus 1 plus c over x plus 1. And that's how you're going to approach that one. Now, C is different. And the reason C is different is because the numerator power is 2. The denominator power is 2. So I can't even do partial fraction decomposition until I do long division. So the first thing I am going to do is long division. So I have x squared plus 2x plus 10 divided into 2x squared plus 4x plus 22. So when I do this, I'm going to match coefficients, so we know it's going to be 2. So 2x squared plus 4x plus 20. Now remember, I subtract off that polynomial from the polynomial up above, and that just gives me 2 as a remainder. So this is the integration of 2 plus 2 over x squared plus 2x plus 10 dx. So much different integration. And I can break this apart, of course, so no problems there. Now, the second term in this integration is when I'm going to have to use partial fractions, so I'm going to focus in on that. And x squared plus, let me lock this rotation again. The x squared plus 2x plus 10 is not factorable over the reals. So x squared plus 2x plus 10, I'm just going to have ax plus b over x squared plus 2x plus 10. And what you see is this really didn't help me. The partial fraction didn't help me. Okay. And the reason the partial fraction didn't help me is because if I multiply by my lowest common denominator, I'm going to get 2 is equal to ax. That means a has to be 0, b has to be 2. So I get 2 over x squared plus 2x plus 10 equals 2 over. So that didn't help me at all. All right, so if that didn't help me, what else can I do? Well, we have learned other techniques of integration. So let's complete the square. So we have 2 over x squared plus 2x plus 1 plus 10 minus 1. And that minus 1 comes from the fact I'm going to take the x squared plus 2x, and I need to complete the square, so that means to add 1, but then I have to subtract 1. So then this becomes 2 over x plus 1, the quantity squared, plus 9. So this is the integration of 2 dx plus. the integration of 2 over x plus 1, x plus 1, the quantity squared plus 9 dx. Now the first integration is straightforward, it's just going to be 2x. Now this looks an awful lot like the tangent inverse, give or take. And what I mean by the give or take is we have this 9 here, and it should have been something squared plus 1. So if I rewrite this as 2 over x plus 1 divided by 3, the quantity squared plus 1, and I'm going to factor out the 9 out of the denominator, then I have plus 2 over 9, the integration of 1 over x plus 1 over 3, the quantity squared plus 1 dx, which looks a lot like the tangent inverse. So this is equal to 2x plus 2/3, the tangent inverse of x plus 1 over 3 plus c. And you're like, wait a minute, why isn't that 2/9? Well, remember, I have to take the derivative of the tangent inverse. So if I do the tangent inverse of u, d du, this needs to be 1 over u squared plus 1 multiplied by u prime, where the derivative of the x plus 1 over 3 is 1/3. I had 2/9, so what I should have started out with is 2/3 to get 2/9 when I got done with the derivative. And that is my answer. Now notice on this one, I didn't actually get to use partial fraction decomposition because it didn't help me. But at this point, we do know how to do other techniques of integration, and so that's why it's in this section. And I did say I was going to give you the answer to the previous one, so let me go back up here and give you the answer to B. When you get done with B, this is equal to negative natural log of x, absolute value, plus 1/2, the natural log of the absolute value of x plus 1, and then plus 1/2, the natural log of the absolute value of x minus 1, and then plus c. Now notice that I have the natural log of x. There's one of my denominators, the natural log of x plus 1. Let me move this over. You can see there's another denominator right here, and then the natural log of absolute value of x minus 1, and there's my third denominator. All right, so let's take a look at, let me see another one that may be of interest. Let's give you the answer. Oh, let's go down to, okay, let me just give you the answers to D, E, and I want to do F. So let me give the answers to D and E. So for D, you're going to take 2 over x minus 2, multiply x minus 4, multiplied by x squared plus 2x plus 6. You're going to have a over x minus 4 plus bx plus c over x squared plus 2x plus 6. This integration becomes the integration of 1 over 30 x minus 4 plus negative x minus 6 over 30 x squared plus 2x plus 6 dx. And when you integrate this, your final answer is going to be 2 over 30, or 1/15. I'm just going to write 1/15. 1/15. The natural log of the absolute value of x minus 4 minus 1 over 30. The natural log of x squared plus 2x plus 6 minus 1 over 3, the square root of 5, the tangent inverse of x plus 1 over the square root of 5, and then plus c. And that is your final answer. So a whole bunch of fun on that one. If you want us to go over that in class, absolutely. Partial fraction on this one would be 2 over x plus 2, the quantity squared. I'm going to factor a negative out of this. So I'm going to make this as a negative 2, x minus 2 is equal to a over x plus 2 plus b over x plus 2, the quantity squared, plus c over x minus 2. When I do this integration, I'm going to end up with the integral of 1 over 16 x plus 2, and then minus 1 over 4 x plus 2, the quantity squared, and then plus 1 over 16 x minus 2 and dx. And this is going to be equal to, when I get totally done, is negative 1 over 8, the natural log of the absolute value of x minus 2, minus 1 or plus 1 over 8, the natural log of the absolute value of x plus 2, and then plus 1 over 4 x plus 2, and this should be minus. So that should be a minus, by the way. That should be minus 1 over 2 x plus 2 plus c, and that is my final answer on that one. Now, let's go ahead and take a look at F and also at G. The reason I want to look at F and G is because they're similar but different. Now, if I say let u equal the cosine of x, and du would equal to the negative sine of x. So then this would become the integration of negative 1 du over, and I would have u squared plus u minus 6. Now, this then is a 1 over, I'm going to use a negative 1 over, I would have u minus 2, u plus 3, which would give me the denominator. So I had a over u minus 1, or u minus 2, plus b over u plus 3. Now notice how I did that by taking the u sub that you would have learned in pre-calculus 1 and realizing the derivative of the numerator would be the derivative of cosine, which would be negative sine. That allowed me to take something that was almost near impossible to integrate into something that is much easier to integrate. And my final answer on this one, after the partial fraction decomposition, is going to be equal to negative 1/5, the natural log of 3 times the tangent squared of x over 2 plus 1, plus 1/5 the natural log of the absolute value of the tangent squared of x over 2 plus 2 plus my constant. All right, let's take a look at G then. With G, the first thing I'm going to do is in the denominator, I'm going to factor the denominator. So I'm going to write this as 1 over, I'm going to factor out x raised to the 1/4. And as you recall, the 4th root of x can be wrote as x raised to the 1/4. So I'm going to factor out an x to the 1/4. This leaves me x raised to the 1/4 plus 1 dx. Now there's a reason I'm doing this, is because at this point I have very little choices of recognizing when I can use partial fraction, when I can complete the square, because I have a square root and a 4th root. Now, if I let u equal x raised to the 1/4, then du is going to be 1/4 multiplied by x raised to the negative 3/4 dx. So I have 4 du is equal to 1 over x raised to the 3/4 dx. Now, what I have then is I have replacements for the du, or the dx. It gets replaced. This gets replaced with 4 du. I have a replacement here. This gets replaced with the u plus 1, and this gets replaced with u. Now, the problem lies in the fact that when I have this 4 and I have u and I have u plus 1, is that my du, I have 4 du, and this is equal to 1 over x raised to the 3/4. Now, this is where the problem is because I now have this x raised to the 3/4, and I don't have it anywhere here. There's no x raised to the 3/4. So I have 4 du, and I'm going to write this x to the 4th as u raised to the 3rd power, dx. And the reason I'm going to do that is because remember that x raised to the 3/4 is the same thing as x raised to the 1/4 raised to the 3rd power. And I have the u is equal to x to the 4th. So that means that 4u cubed du would equal to dx. So I need a 4u cubed du. Now you can see that I'm going to end up with 4u squared over u plus 1 du. Now, don't forget, the numerator is a higher power than the denominator, so the first thing I'm going to need to do is long division. U plus 1 divided into u squared plus 0, u plus 0. I'm going to ignore the 4 because I'm going to bring that out as a constant. Now, to get from u to u squared, I need to multiply by a u, leaving me u squared plus u. Don't forget, I am now subtracting this off, so this becomes negative u plus 0. That means I need a negative 1, so I have negative u minus 1. Changing my signs because I'm going to subtract that off. I get 1, so I end up with 1 over u plus 1. So this becomes 4. The integration of u minus 1 plus 1 over u plus 1 du. When I do this integration, I'm going to get 4u squared minus, oh wait, I'm not going to get 4. It's going to be 2u squared minus u multiplied by 4, so 4u. And then it's going to be plus the natural log of the absolute value of u plus 1 plus c. Now don't forget, I do need to go back and substitute. I had my substitution of u being x to the 1/4, so it's 2 x raised to the 1/4, the quantity squared, minus 4 x raised to the 1/4, plus the natural log of the absolute value of x raised to the 1/4. Oh, there should be a 4 there. Don't forget there is a 4 on that one too. Plus 1 plus c, and that is my final answer. Now let's take a look at our last example here, which is e to the x divided by e raised to the 2x minus 4. And the first thing I'm going to do is a u sub as well. I'm going to come down here and I'm going to say let u equal e to the x, and du is equal to e to the x dx. So my integration of e to the x over e to the 2x minus 4, the quantity squared, dx becomes, this gets replaced with, and don't forget the dx, gets replaced with a du. This gets replaced with u squared. So what I have is the integration of 1 over u squared minus 4, the quantity squared, du. But u squared minus 4, the quantity squared, factors, so this becomes 1 over u minus 2, u plus 2, the quantity squared, du. So this becomes 1 over the integration of u minus 2 squared, u plus 2 squared du. Once again, I do my partial fraction, so I have 1 over u minus 2, the quantity squared, u plus 2, the quantity squared, is a over u minus 2, plus b over u minus 2, the quantity squared, plus c over u plus 2, plus d over u plus 2, the quantity squared. What this then becomes is my a, which is over the u minus 2, is 1 over 32, u minus 2. My b, which is over the u minus 2, the quantity squared, is 1 over 16, u minus 2, the quantity squared. My c, which is over the u plus 2, becomes 1 over 32, u plus 2, and then my last one is 1 over 16 u plus 2, the quantity squared. Now, when I get done with this integration, I'm going to end up with 1 over 32, the natural log of the absolute value of e to the x plus 2, minus 1 over 16 e to the x plus 2, plus 1 over 32, the natural log of the absolute value of e to the x minus 2, minus 1 over 16 e to the x minus 2 plus c. And that is my final answer. And that's how come on some of these tests you'll only see 3 integrations, is because the length it takes to complete one of the integrations. And that's it for this video.